Chapter 1. The Messenger That Never Rests. Light enters our lives so quietly that we rarely notice its arrival. It lies across the floor at sunrise, trembles on the surface of water, and disappears into the pupil of an eye. Yet behind this familiar brightness hides one of the longest and most beautiful mysteries in science. For thousands of years, people used light without knowing what it was. Sailors trusted the stars, farmers watched the changing length of shadows, and priests arranged temples so that the rising sun would illuminate a sacred chamber on a particular day. Light was a guide, a clock, a warning, and sometimes a god. The mystery seemed simple at first. Was light something that traveled from objects into the eye, or did the eye send something outward to touch the world? Was it a stream of tiny objects, a vibration passing through space, or something for which human language had not yet created a name? The answer would not come from one person or one century. It would pass from Greek philosophers to Arab scholars, from darkened rooms to royal academies, and from glass prisms to quantum laboratories. Every generation would capture one face of light, only to discover that another face was still watching from the shadows. Chapter 2. Eyes That Reached Into the World. Some ancient Greek thinkers imagined vision as an active power. Empedocles suggested that a kind of inner fire emerged from the eyes and met the light outside, while Plato described sight as a union between visual fire and daylight. To them, looking was almost a physical gesture, as though the eye extended an invisible hand toward an object. The idea felt convincing because vision obeyed the direction of the gaze. Turn your eyes toward a flame, and the flame appears, but turn away, and it vanishes from your experience. The speed of sight also seemed immediate, since the stars appeared the moment a person opened their eyes. Other thinkers were less satisfied. Aristotle argued that light was connected to a transparent medium made active by a luminous source, although his explanation was very different from modern physics. He understood that vision required a relationship between the object, the surrounding medium, and the observer. Euclid approached the problem geometrically. In his work on optics, he treated vision through straight lines and angles, creating a mathematical language for perspective and reflection. Even though his rays were linked to vision rather than modern light, his geometry became a tool that later scientists could preserve after the old philosophy had faded. Chapter 3. Mirrors, Empires, and Measured Rays. In Alexandria and other centers of the ancient Mediterranean world, optics became increasingly practical. Engineers studied mirrors, physicians examined the eye, and astronomers needed accurate lines of sight to measure the heavens. Light was no longer only a subject for philosophers, because empires also needed instruments. Hero of Alexandria described devices involving mirrors and reflected images. Stories later grew around ancient burning mirrors that could supposedly set enemy ships on fire from a distance. The most famous legend connected such a weapon with Archimedes during the Roman siege of Syracuse. Whether Archimedes truly burned ships with reflected sunlight remains doubtful. Modern reconstructions show that concentrated mirrors can ignite materials under favorable conditions, but doing so against moving ships would have been extremely difficult. The legend survived because it gave light the dramatic power of a weapon. Claudius Ptolemy studied reflection and refraction during the 2nd century. He measured how rays changed direction when passing between air, water, and glass, although his mathematical rule was not completely correct. His effort was still remarkable because it treated light as something whose behavior could be tested rather than merely discussed. Ancient optics therefore left two inheritances. One was a collection of mistaken ideas about rays emerging from the eye, while the other was a powerful geometry of straight paths, angles, mirrors, and lenses. Centuries later, a scholar in Cairo would separate these inheritances and rebuild the science of vision around experiment. Chapter 4. Ibn al-Haytham and the Darkened Room. Hassan ibn al-Haytham was born in Basra during the 10th century when scholars across the Islamic world were translating, preserving, and challenging Greek science. Mathematics, medicine, astronomy, and philosophy traveled between libraries from Baghdad to Cairo. Light became one of the subjects through which the ancient world could be questioned. A famous later account says that Ibn al-Haytham proposed a plan to control the flooding of the Nile. After reaching Egypt, He supposedly realized that the project was impossible with the available technology and feared the anger of the Fatimid ruler al-Hakim. According to the story, he pretended to be mentally unwell and lived under restricted conditions until the ruler died. Whatever the exact truth of this dramatic episode, Ibn al-Haytham spent years studying vision and light. His book of optics examined reflection, refraction, shadows, color, lenses, and the anatomy of the eye. He rejected the idea that the eye sends rays into the world and argued that vision occurs when light from external objects enters the eye. One of his most memorable tools was the dark chamber, later associated with the camera obscura. Light entered through a small opening and formed an inverted image on the opposite wall. The image showed that light traveled along definite paths, and that rays from different parts of an object could cross without becoming confused. Ibn al-Haytham also gave experiment a new authority. A respected philosopher could be wrong, while a carefully arranged observation could reveal the mistake. Light had become more than a metaphor for knowledge because its study was helping to create a new method of acquiring knowledge. Chapter 5. Light returns to Europe. Arabic works on optics entered medieval Europe through translation centers in places such as Toledo. Ibn al-Haytham became known in Latin as Alhazen, and his ideas influenced scholars including Roger Bacon, Whitelaw, and John Peckham. Knowledge crossed religious and political borders even when armies and rulers remained in conflict. Medieval scholars studied rainbows, mirrors, lenses, and visual perception. Their work gradually improved spectacles, which appeared in Europe near the end of the 13th century. A philosophical question about the nature of vision had produced an object that allowed aging eyes to read again. During the Renaissance, artists became experts in the geometry of sight. Filippo Brunelleschi demonstrated linear perspective, while painters used mathematical depth to transform flat walls into imagined spaces. The laws of vision became tools for architecture, theater, painting, and political spectacle. Johannes Kepler completed a crucial part of the story in the early 17th century. He explained that the eye forms an inverted image on the retina and separated the optical formation of an image from the mind, interpreting it. The eye was no longer a mysterious source of visual power, but a living optical instrument. Chapter 6. The Bent Path. A ray entering water does not continue in exactly the same direction. A straight stick placed in a glass appears broken, a swimming pool looks shallower than it is, and a coin hidden behind the edge of a cup can reappear when water is added. These ordinary illusions are signatures of refraction. Willebrord Snell studied the mathematical relationship between the angles of incoming and refracted light in the early 17th century. His result was not published during his lifetime, but the rule later became known as Snell law. René Descartes published the same mathematical relationship and tried to explain it through a mechanical model of light. Pierre de Fermat offered a more elegant principle. He proposed that light follows a path requiring the least travel time, although the most precise modern form refers to stationary optical time. From this principle, the law of reflection and the law of refraction could both be derived. The idea was strangely poetic. Light behaved as though it surveyed many possible roads and selected the one demanded by nature. It did not think or plan, but mathematics made its journey look almost purposeful. Chapter 7. Newton opens the white door. In the 1660s, Isaac Newton darkened a room and allowed a narrow beam of sunlight to enter through a small opening. He placed a glass prism in its path and watched white light unfold into a band of colors. Red, orange, yellow, blue, and violet appeared like hidden provinces inside a color that had seemed simple. Many people believed that the prism colored the light. Newton tested this by isolating one color and passing it through another prism. The second prism changed the direction of the ray, but did not turn red light into blue or blue light into red. He then recombined the separated colors and produced white light again. Whiteness was not purity in the sense people had imagined, because it contained a multitude. The prism had not painted sunlight, but had revealed its internal diversity. Newton favored a corpuscular description of light. He imagined extremely small particles traveling from luminous bodies, and used this model to explain straight-line propagation and reflection. His scientific authority gave the particle view enormous influence in Britain, yet the theory faced difficulties. It could not easily explain every pattern near edges, every colored band, or the strange behavior of light in certain crystals. Newton had opened the white door, but the particles he sent through it were not the only possible inhabitants. Chapter 8. Huygens and the Ocean of Space. Christian Huygens saw light differently. Instead of a shower of particles, he imagined a disturbance spreading through a medium, much as sound spreads through air or ripples move across water. Each point reached by a wave could become the source of new secondary waves. This principle allowed Huygens to construct advancing wave fronts. Reflection and refraction emerged from geometry, and the slower propagation of light in denser optical materials fitted the wave model. Newton and Huygens could explain some of the same phenomena while imagining completely different realities. Huygens also studied Iceland spar, a transparent crystal that produces two images of a single object. The crystal divided incoming light into an ordinary ray and an extraordinary ray. This double refraction suggested that light possessed hidden directional properties. The wave theory remained less influential than Newtonian corpuscles for many years. Newton was a towering figure, and scientific communities are not immune to prestige. Sometimes an idea must wait not because it lacks truth, but because another voice fills the room. Chapter 9. Young and the Two Openings. Thomas Young was a physician, linguist, and natural philosopher with interests ranging from the human eye to ancient Egyptian writing. At the beginning of the 19th century, he turned to the question that had divided Newton and Huygens. He believed that light could interfere with itself like overlapping waves. Imagine two sets of ripples spreading across a pond. Where two crests meet, the water rises higher, while a crest meeting a trough can produce calm. Young proposed that light could create the same pattern of reinforcement and cancellation. In his famous experiment, light reached two narrow openings and then traveled toward a distant surface. Instead of producing only two bright regions, it formed alternating bright and dark bands. Darkness appeared in places where light from the two paths canceled. The dark bands were difficult to explain with independent classical particles. Two sources of light were producing less illumination than one might produce alone. The result made sense if light carried phase, allowing one wave to oppose another. Young presented his work in Britain, where Newtonian ideas still commanded deep loyalty. Some critics dismissed or mocked his conclusions, but the pattern remained. On the screen, light had written an argument more persistent than reputation. Chapter 10. Fresnel and the Bright Point in the Shadow. Augustin Jean Fresnel entered optics during a period of political upheaval in France. Trained as a civil engineer, he studied diffraction, the spreading and bending of light near edges and openings. He combined experiments with mathematics and developed a powerful wave theory. In 1818, Fresnel submitted a study of diffraction to a competition organized by the French Academy of Sciences. Siméon Denis Poisson, who supported the particle view, examined Fresnel equations and found what seemed to be an absurd consequence. The theory predicted a bright point at the center of the shadow behind a small circular obstacle. Dominique François Arago performed the experiment. A bright point appeared exactly where the wave calculation predicted it. The supposed objection became one of the most memorable victories of wave optics. The central spot did not prove that every old particle idea was impossible, but it transformed the balance of evidence. Waves could enter the kingdom of shadow and place a tiny lantern at its center. Newtonian corpuscles began to lose their throne. Chapter 11. Polarization and the Direction of Light. Ordinary sunlight vibrates in many transverse directions. Under certain conditions, however, those vibrations can be selected, producing polarized light. Reflections from water, glass, roads, and painted surfaces can favor particular orientations. Etienne Louis Malus discovered in 1808 that reflected light could possess a preferred direction. He reportedly noticed the effect while looking through a crystal at sunlight reflected from windows in Paris. A casual view across a city helped reveal a hidden order inside light. Fresnel and Arago studied polarization and interference in greater detail. Their results showed that light waves had to be transverse rather than longitudinal, like ordinary sound in air. The oscillation occurred across the direction of travel. Polarization eventually left the laboratory. It became useful in mineralogy, photography, chemistry, astronomy, and stress analysis. Modern polarized sunglasses reduce glare because they block much of the horizontally polarized light reflected from roads and water. A pair of sunglasses therefore contains the memory of a centuries-long debate. When glare disappears as a lens is rotated, the directionality of light becomes visible through its absence. An abstract property turns into a quieter view of the world. Chapter 12. Maxwell unites electricity, magnetism, and light. By the 19th century, electricity and magnetism had become major sciences. Michael Faraday showed that changing magnetic conditions could produce electric effects, and he imagined lines of force extending through space. His experimental vision suggested that empty space was not truly empty of physical structure. James Clerk Maxwell translated these insights into mathematics. His equations described electric and magnetic fields generating and sustaining one another. When he calculated the speed of the resulting waves, the value was remarkably close to the measured speed of light. The conclusion was revolutionary. Light was an electromagnetic wave, joining electricity, magnetism, and optics in one theory. A spark, a magnet, and a sunbeam had become expressions of the same underlying field. Maxwell did not merely add another explanation of familiar light. His equations predicted a much larger family of invisible electromagnetic waves. Visible colors occupied only a narrow region in a spectrum extending far beyond the limits of human sight. The triumph seemed complete. The wave had defeated the corpuscle, and light had found its place inside one of the greatest unifications in physics. Yet nature was preparing another reversal. Chapter 13. Invisible kingdoms, human eyes evolved to detect only a small portion of electromagnetic radiation. Beyond red lies infrared radiation, while beyond violet lies ultraviolet radiation. Farther outward stretch radio waves, microwaves, X-rays, and gamma rays. William Herschel discovered infrared radiation in 1800 while measuring temperatures across a spectrum produced by a prism. The thermometer became hottest just beyond the visible red region. An invisible form of light was carrying heat where the eye saw darkness. Johann Wilhelm Ritter soon investigated the region beyond violet. He found that invisible radiation there could darken certain chemical materials more effectively than visible violet light. The spectrum expanded in both directions. Heinrich Hertz later generated and detected radio waves, confirming Maxwell's prediction. Sparks in one part of his apparatus created electromagnetic waves that produced effects elsewhere. Light and radio had become relatives separated mainly by frequency and wavelength. Hertz also noticed that ultraviolet light could make sparks occur more easily between metal electrodes. He did not yet possess the theory needed to explain the effect. A small experimental curiosity was pointing toward the return of the particle. Chapter 14. The furnace that broke classical physics. At the end of the 19th century, physicists studied the radiation emitted by hot objects. A piece of metal begins dark, then glows red, orange, yellow, and eventually white as its temperature rises. Scientists wanted one equation that could describe the full distribution of this thermal light. The idealized object was called a black body. It absorbed incoming radiation and emitted a spectrum determined by its temperature. Experimental measurements were precise, but classical theories failed to describe the entire curve. One classical calculation predicted that a hot body should release enormous amounts of energy at very high frequencies. The prediction became known as the ultraviolet catastrophe. Nature did not behave this way because furnaces did not pour infinite energy into invisible ultraviolet radiation. In 1900, Max Planck found a formula that matched the observations. To derive it, he assumed that energy exchanges occurred in discrete portions related to frequency by a new constant. Energy could not always be divided into arbitrarily small amounts. Planck initially treated quantization cautiously and did not immediately imagine light itself as a stream of particles. He had introduced a mathematical key without fully accepting the door it would open. The reluctant step became the beginning of quantum physics. Chapter 15. Einstein brings back the particle. In 1905, Albert Einstein worked at the Swiss Patent Office in Bern. Far from the grandest university positions, he published several papers that transformed modern physics. One of them proposed a radical interpretation of light. Einstein argued that light energy could behave as if concentrated into individual quanta. The energy of each quantum depended on the frequency of the light. Higher frequency radiation carried larger individual packets. This idea explained the photoelectric effect. When light strikes certain materials, electrons can be released, but only if the light frequency exceeds a threshold. Increasing the brightness of light below that threshold does not provide each electron with the necessary energy. A wave-only description suggested that intense light should gradually deliver enough energy, even at low frequency. Einstein instead described an encounter between one light quantum and one electron. The electron received energy in a concentrated transaction rather than through a slowly accumulating ocean. Einstein later received the Nobel Prize especially for the law of the photoelectric effect, not for relativity. The quiet metal surface had provided the evidence honored by the prize. Light had returned wearing the face of a particle, but it had not surrendered its waves. Chapter 16. Millikan tests an idea he disliked. Robert Andrews. Millikan was not initially convinced by Einstein's light quantum hypothesis. The proposal seemed to conflict with the powerful evidence for wave behavior. Rather than accepting it, Millikan designed careful experiments to test its predictions. For years, he measured the energies of electrons released from illuminated metals. The relationship between light frequency and electron energy matched Einstein's equation with striking accuracy. The experiment confirmed a theory that its own experimenter found difficult to believe. This episode reveals an important strength of science. A researcher does not need to admire a theory in order to test it honestly. Personal expectation can lose before a sufficiently disciplined measurement. The result also sharpened the mystery. Interference required an extended wave description, while the photoelectric effect revealed localized energy exchanges. Light was refusing to choose the single identity that classical language demanded. Chapter 17. Compton and the Collision of Light. In the early 1920s, Arthur Holly Compton directed X-rays at matter and studied the scattered radiation. He found that some X-rays emerged with longer wavelengths. The change depended on the scattering angle. Compton explained the result as a collision between a light quantum and an electron. The photon carried energy and momentum, transferred part of them to the electron, and continued with reduced energy. Light behaved like a participant in a mechanical impact. The experiment was powerful because it extended particle behavior beyond the photoelectric effect. The photon was not merely a bookkeeping device used when matter absorbed radiation. It could enter a collision and leave with altered momentum. Compton received part of the 1927 Nobel Prize in Physics for the effect bearing his name. By then, the word photon was entering scientific use. The particle of light had gained not only evidence, but an identity. Chapter 18. One photon, two paths. The double-slit experiment became even more mysterious when performed with extremely faint light. Individual detections appeared as separate points on a screen. Each event looked particle-like and localized. As more events accumulated, the points gradually formed an interference pattern. The final distribution was shaped like a wave pattern even when detections occurred one by one. Each photon arrived at one place, yet the probabilities carried information about both openings. Trying to determine which opening the photon used changes the result. When the experimental arrangement reveals reliable path information, the interference pattern disappears. The observer does not need to be a conscious person because the decisive factor is the physical interaction that records the path. This is sometimes misunderstood as proof that the human mind creates reality by looking at it. Quantum theory does not require a person to stare at the apparatus. A detector, surrounding environment, or measuring device can establish the relevant interaction without human awareness. The mystery is therefore not a magical power of consciousness. It is the fact that the conditions used to ask a physical question help define which properties can appear. Nature answers the experiment that is actually built, not every experiment that could have been built. Chapter 19. Beyond Waves and Particles. Niels Bohr developed the principle of complementarity. Wave and particle descriptions reveal different aspects of quantum phenomena, and the experimental arrangement determines which aspect becomes accessible. Neither classical image alone captures the complete quantum object. A photon is not simply a tiny classical ball that secretly travels along one definite route. It is also not merely a classical water wave spread through space. It is a quantum excitation of the electromagnetic field described through amplitudes, states, probabilities, and interactions. Quantum electrodynamics later provided an extraordinarily precise theory of light and charged matter. Richard Feynman, Julian Schwinger, and Shinichiro Tominaga developed methods that successfully calculated effects once threatened by mathematical infinities. Their work turned the mystery of light into one of the most accurately tested structures in science. Even this powerful theory does not replace wonder with an ordinary picture. Its equations predict results with astonishing precision, but everyday imagination still struggles to represent what the equations describe. Light can be calculated more easily than it can be pictured. Perhaps this is why the old question remains useful. Asking whether light is a wave or a particle exposes the limits of concepts created from everyday objects. The final answer is not that light changes costumes, but that nature was never required to fit either costume completely. Chapter 20. The light inside the modern world. Einstein's idea of stimulated emission eventually helped make the laser possible. After work on masers and atomic amplification, Theodore Maiman demonstrated the first working laser in 1960 at Hughes Research Laboratories. A ruby crystal produced a concentrated pulse of coherent red light. Laser light differs from the mixed radiation of a candle or ordinary lamp. Its waves can possess a highly organized relationship of frequency, phase, and direction. This coherence allows lasers to cut materials, read data, perform surgery, measure distance, and examine atoms. The photoelectric effect lives inside cameras, light sensors, automatic doors, and solar cells. Fiber optic cables guide light across continents and beneath oceans, carrying messages as rapid patterns. Much of the digital world travels as controlled brightness through transparent glass. Modern experiments also use entangled photons. Work by John Clauser, Alain Aspect, Anton Zeilinger, and many others tested quantum correlations and helped establish quantum information science. Light now carries not only images and conversations, but quantum states that may support new forms of communication and computation. The story ends where it began, with a beam crossing a darkened room. To the eye, it may seem simple, but inside it lived the geometry of Euclid, the experiments of Ibn al-Haytham, Newton colors, Huygens waves, Young bands, Maxwell fields, and Einstein quanta. Light is both our oldest messenger and one of nature's most subtle secrets, always arriving, always revealing, and never surrendering all of itself at once. Ключевые части фотоэлектрическом эффекте Комптона, квантовой оптики и фотонной интерференции основаны на материалах Nobel Prize и NIST.